Verilog series, we will be discussing about design and simulation of a parameterized digital clock, which will have hours, minutes, and seconds. Most of you might have seen these type of clocks in your house. You might have not known how these clocks work. Today, we'll be understanding how we can design such a clock using Verilog coding and simulate it. The key features are going to be parameterized frequency divider. That means we are going to simulate this clock on our FPGA. 24-hour format, logic handling transitions for seconds, 60 and minutes. Asynchronous reset ensures a known starting state, that is your state is starting from 0000. Scalable simulation, test bench optimized for rapid verification using parameter overriding. Let us see what is that. First, to understand, we need to understand what is frequency division. The problem is most FPGA run at megahertz frequencies, example 50 megahertz or 100 megahertz. But a clock needs only 1 hertz pulse. So you need to bring down that 50 megahertz to 1 hertz. How do you do it? An internal 26-bit register ticker counts cycles up to tick limit. Tick limit here will be, if you have 50 megahertz, it will be around 499999. We'll be discussing about that in while we discuss the code. F out. That means your frequency that you need to get as an output. That is the 1 hertz pulse. You have Fin and tick limit plus 1. This is the formula. Implementation. Once ticker reaches the limit, it triggers the click wire and resets. Here, our input is for 50 megahertz, and the limit is minus 1 of this tick limit. So, the resultant, whatever we get out of this formula, will be equal to 1 hertz. The RTL design, the nested condition logic. What we will do is it will increment every click and it will reset at 59 because you have 60 seconds, right? So it will count from 0 to 59. At the 59 second after it is done, it will reset. In the same way, it will increment only when seconds. Here also it is 59 and click goes high. Click is nothing but for your good understanding, I'll explain it in the code itself. So what happens here, once we have done the frequency divisor, we use that whenever your ticker has reached your tick limit. What is my tick limit here? I have given my tick limit as 499999. That means 50 megahertz minus 1. This is my limit. So if it reaches that, the click flag will go high. This is what the click we are talking about. Hours, it will always increment only when minute is equal to 59. So and second is also equal to 59 and click is high. So this is how we'll handle it. Here you can see it using the Verilog code. If click is high here, that means the ticker has reached the tick limit. What we will do is we will reset it. It will become 0. Here again minute will become 0 and hour also will become 0. If the if the here we have the if condition, right? If this is not, it means just if the click is not 1, we'll have hour is equal to hour plus 1, minute is equal to minute plus 1, and second is equal to second plus 1. This is how the code is going to run. And modulus handling, explicit check for hour is equal to 23 because we have 0 to 23, right? Then it will wrap back to 0. Verification strategy, simulating 86,400 seconds at 50 megahertz would take a long time and generate a massive wave file. Parameter overriding, what we'll do is the tick limit is what we are using in the test bench. That will ensure that this forces the clock to increment every single clock cycle, allowing a full 24-hour cycle to be simulated in less than 1 millisecond of simulation time. What I mean to say here is, if I want to do this at 50 megahertz, so at every second it will take the whole day to simulate this one test bench, right? So what I am doing is I'm using tick limit. Once I use this tick limit, this will force the clock to increment every single clock cycle, allowing a full 24-hour clock cycle to be simulated less than 1 millisecond. Now let's go to the code. First, let's see the design part of the code. Okay. Now this is my module for digital clock. I have given the time scale here, and I've set the parameter as tick limit. Input clock, input reset, and output regis. This is for the second, minute, and hour. Here we have a 6-bit register because for second and minute as they need to reach till 59, but for the hour it is only 23, right? Because you have only 24 hours, so 5 bit is enough. Then we have a 26-bit ticker that will count this till it reaches this tick limit. So now we have a frequency divider working here, always at positive edge of the clock or positive edge reset. If reset is high, ticker will be 0, or else, that is else if ticker reaches the tick limit, then again ticker will become 0. Else ticker less than ticker plus 1 means it will increment. I can write here that it is incrementing. Now assign click is equal to, so what is click? Click is required because if by chance my this ticker reaches this limit, that means it has completed 1 day. So what I will do is I will reset all the second, minute, and hour parameters. It will all become 0. They'll start fresh. So this is a use of click. Now we'll go to the timekeeping logic, how the timing works. Always at positive edge of the clock or positive edge reset begin. We'll set one reset button so that we can set all the timings to 0000. And else if click begin. So what I mean to say here is, if click is high and also if second is equal to 59, we will again reset it. It will become second. Then if minute is also equal to 59, and if click is high, in any one of this case, either click is high or minute becomes 59. That means 60 minute completed, this minute will again become 0. Because when you are doing a clock, you might finish like, now you can, let's consider time to be 10 o'clock. Now it will go till 10:59. Again you want the clock to reset, right? The minute hand should again start from 0. So that is where this will be helpful. And this hour hand will be helpful when you complete 1 day, and this will be helpful when you complete 1 minute. Now if this click is not given, what should I do? I should keep incrementing my hour, minute, and as well as second. This is how your typical clock works. You would have understood that. Now we'll simulate this design. What we need to do is, we have the module test bench digital clock. All the inputs will be registered and the output will be given in the form of wires. Whatever you have done here, same you write it down here. Now you need to instantiate this clock. But here your one thing you have to import, this is very important. Whatever I have highlighted, it's very important. Instantiate design under test or unit under test with tick limit is equal to 0. So even though I have given my tick limit to be 4, that's 50 megahertz minus 1, I need to set it to 0, because what will happen is if I keep this, this simulation time will run for the whole day. I cannot complete it within seconds. It will take me the whole day to show you the output. So what we do here is we'll set the tick limit to be 0. Now I have my clock that is of 10 nanoseconds period. That is 5 nanoseconds will be positive and 5 nanoseconds it will be negative. For the first condition, my clock is 0 and reset is equal to 1. As soon as my reset is equal to 1, all these parameters will become 0, 0, 0, 0. Here also, here also. Now my clock is starting fresh. Let us go. Where is that? Okay. It will be somewhere here. Yeah. Once the reset is set, it will become 0. Now I'm telling after 20 clock pulse, like 20 nanoseconds, because I have given a time scale as 1 nanoseconds, right? So after 20 nanoseconds, reset is 0. That means I have changed my condition to be 0. Now this operation will start. See the design here. If reset is not 1, this whole this code will run. That means our clock will start incrementing. So it increments 0, 0, slowly it will increment. Then yesterday, some of my juniors had asked me this doubt. They understood all this, but they were not able to simulate it. One thing that you have to do here is, 1 minute. Yeah. Here you have to select Aldec Rivera Pro. Then here it will be system verilog and slash verilog. Then you have to click on open EPWave after run. This is not necessary because here we are not checking any waveform. Here just we are running it. Let us save it once. See, here you might have seen a problem. I have given that the clock should run till 8,64,000. This means it has the number of seconds that it has to run. It takes around these many seconds to complete one day. Now the problem is this EDA playground will limit your simulation lines. That means I can go up to a certain limits, like these many number of lines I can show output, but more than that EDA playground will not allow me. So what it is trying to do is a result reached the maximum of 5,000 lines. Till 5,000 lines, this has covered all the possible outputs. But after that 5,000 lines, it is not able to cover it. But the code is correct and it will run up till 8,64,000. If you use any better EDA tools like Xilinx Vivado or Xilinx ISC, you can go up to this. You can complete the whole simulation. I hope you understood how to do this project. It's a very small project. If you have any doubts, feel free to put it down in the comment section. Thank you.